Ben Smith in here afterwards. Does he use the board?
Only lightly. He uses the projector, but he'll use the sides. Other times he'll just draw on his tablet, but it's kind of just 50-50. Why do you ask?
Because those markers stink.
Yeah.
And I want to get, I'm going to talk to him to go over to the bookstore and just get a bunch of good ones for all these out.
Mm-hmm.
Anyway, first thing I always do is, looks like we got a full house down, 2, 4, 6, 8, 10, 12. Well, I think we're missing 2, but don't hold me. Kind of, it started 14 people. Now there's 12 in here. There may be more coming. Anyway, first thing, oh yeah, I ate something last night. And I'm not feeling real well. If I have to leave and just vomit or something, forgive me. But anyway, questions about anything? I always take questions. Because there's wrong answers in the book for several of those exercises. Did anybody else notice that besides me? We're going to do some. Any questions at all? That's great. Okay, that's fine. Well, I have problems to do. I want to do 1-7.2 first, but I'm trying to, the way I'm trying to do this is just go through the problems, discuss it, and I'll add little things, permutations and things like this that would complicate it. I can tell you that in the book, he tries to make the problems fairly simple, but small things that change can make them very complicated. And I'm just warning you, you can't get real relaxed about this stuff. You have to be attentive. So do you have 1-7.2 or do I need to?
Yeah, I don't know.
Okay. You do? Okay.
A certain typist sometimes makes mistakes by hitting a key to the right or left of the intended key.
Wait a second. This is 1-7.2 exercise. Sorry. That's the problem.
Okay. I'll be fine.
I want to do the exercise first. The problems, they go into a little more detail, but most of the time, if you see the exercises, the problems just, you don't have a problem. You don't have difficulty with it.
A manufacturer of electronic equipment purchases 1,000 ICs from supplier A, 2,000 ICs from supplier B, and 3,000 ICs from supplier C. Testing reveals the conditional probability of an integrated chip failing during burn-ins for device from each of the suppliers. The failure rate for A is 0.05, probability of failure for B is 0.1, and the probability of failure for C is 0.1.
We could extend this. We could have different failure rates. We could have more. Everybody follow me on this? This would be a logical thing to be prepared for an exam. Okay, if we have this, the first thing I'm going to do is find out the total number that failed. First, the total number. And the total number of actual components you have is 3,000. Everybody agree with that? That should be, just add them up, right? You got 1,000, 2,000, 3,000, right? I mean, does everybody follow me on this? You're very quiet today.
Well, wouldn't that be 6,000?
Or 6,000. Now I'm glad you said that. And I'm glad I said it. Yeah, 6,000. So total number N is going to be 6,000. Now from that, the number that fail, well, this is the way I do it. Take 1,000 divided by 20, because 0.05 is 1 over 20. If you get that, that's going to be what, 50, isn't it? Fail A is going to be 50, and then number that fail B is just 200, and number that fail C is going to be 300. So the total number that fail is going to be 550. Do you agree with this, class? And yell at me if I made a mistake. Okay, that's the total number. Now, getting back to the question, what does he say?
They're all mixed together and one device is selected at random. What's the probability that it will fail during burn-in?
now this is a straightforward problem, it's just the relative frequency. But by the way, how many looked at this? I'm hoping you do, and I'm gonna encourage you to do this, because on quizzes, tests, and stuff like this, if you have any kind of lack of understanding of some concept, generally speaking, it will cause a catastrophic event. You will mess up everything. This course especially. All right, so if I just mix them all up together, and I know I got 550 bad ones, and I have 6,000 good ones, in terms of the relative frequency approach, the probability of the thing would fail during burn-in is just going to be equal to the total number that are failed, 550, if they're all mixed up, divided by the total number, or 6,000. And that's what, 55 over 600, so 11.
Over 120.
And, you know, I think they give that in terms of the decimal number.
I do.
0.092.
Now, I'm gonna tell you, your calculators, and you're allowed to use calculators in this class for the actual quizzes and tests. If you look, you have to make sure you have enough decimal points, because those two answers for this one are like 0.09, and the difference is in the second and third digit. And I have that written down. Let me just, 0.09167, is that right? Now, the second part, B, go ahead.
Given that the device fails, what's the probability that the device came from supplier A?
This one I'm gonna do if we have a probability of, now, first, the device fails, and we want to know what the probability of that is, that it came from A, right? So I'm going to draw this with I'm going to use the Venn diagram logic on this one, but it's pretty straightforward. It's actually a good way to start thinking about this. So I know that that is really probability of A, and it's really going to be intersect the failed devices over probability of a device failing. I'm not writing this in a real strict sense mathematically, but can you follow my logic on this? So we find, if it is in A, how many total fail? That would be the intersect of failure and A. And what is that, 50? And the total amount that failed are 550. Now that number is 0.9091, I think, as I recall. Can anybody confirm that?
Yeah, that's correct.
Do y'all with me on this, class? And now I have a question. All right. This is where people can, look at this and say, I got it, no problem. Now suppose I change it up a bit. Suppose I'm going to say that I've got a device that works. You with me? Can y'all follow me? I'm going to select one at random and it works. What's the probability that it came from A? Think about it. What did we just calculate? Let me ask you. If it fails, that it came from A, right? Now we're saying if it works, it came from A. How would you do that problem? I'm just trying, I'm not asking you to do it entirely, just talk to me about it. How would you do it?
I'd probably start with this second part here, so the probability of A given that it was good.
We want probability A, given it's good, the probability it came from A. You follow me on this? So what do you need to do on this? You're right.
I would find the number of good parts
In,
for each, like A, B, and C.
right, and what would it be? One, it would be what, 6,000 minus 5, or 6,000 minus 550, right? Y'all follow me? I don't have to do this one, just make sure you can think this through, because here's what happens on a quiz or test. All right, you're real comfortable with the first part, I got it. Change it up a little, and you mess up. I promise you, I see this all the time in this class, and it drives me nuts, because I don't know how to correct, I shouldn't say it all the time, but I see it more often than I care to. All right, so the total amount of good ones is gonna be 550, right? I'm sorry, 6,000 minus 550. That's the total number of good ones. Now, what's the probability it came from A? Let's just do it. And I hope you follow me on this one. So this is probability, it came from A and it's good, over the probability it's good. So for the lower one, that's gonna be 6,000 minus 550. First, does everybody agree with me? I could draw a Venn, but I think at this point you should have it. Now, what goes up here? That's right. It's 1,000 minus 50. I don't know what it is, but can you tell me? And write this down, because you should be able to take the next logical permutation, go to B, given that it's good, it came from B, given that it's good, it came from C, right? And if you add that up, it has to be 1, the probabilities. Do you have a number for this?
0.1743.
And if you do, we assume we selected a good one, right? If you take a look at this and you go to B intersect G, C intersect G, if you add up all those probabilities, it has to be 1. If it's not, you made a mistake somewhere. Just to keep your head on straight. Are you good with this one? I get problems like this, and I'll tell you the truth. Sometimes I don't know what they're trying to do. I see all sorts of numbers. I can't figure out the logical progression. But I'm trying to make it clear. All right, we're going to move on. Now, we do have Monday off, I think.
Mhm.
And unless I'm mistaken, I heard the weekend is going to be rainy.
Yeah.
I mean, that's what I saw today. And I think, what is that? WRBL's website. All right, now, next one. Okay, we're talking about independence. And this is going to be, what is it, section 1.8, I think, 1-8. All right, independence, this is going to be something that is not always obvious. And first I'm going to say that, you know, if you have the general form from the Venn diagram, and we're taking a look at the probability of A, and this is going to be, A intersect B. I want to do this first this way. We know if they are independent, and let's assume we're talking about A independent of B. If we look at this, then this will be just probability of A times probability of B. Good example of that. Take a die and roll it twice. Outcome of the first one is going to be A, outcome of the second roll B. This is as simple as it gets. No matter what you roll the first time, if it's a fair die, the second time you roll it is independent. It doesn't matter what the outcome of the first one is. Does everybody follow me on? That would be independent events. I gave another example. If you have throwing a die, and of course the outcomes could be from 1 to 6, and then tossing a coin. You can only get heads and tails. One has no effect on the other's outcome. Everybody with me? So this is independent in the general sense. And it means this will be true. Now that's real important, if they are independent. If you look at that, then if you look at the probability of A union B, that's going to be probability of A, this is only for independent events, plus probability of B. Now remember, this is something like an OR gate. Either or happens, the outcome counts. Follow me? It's a positive. But then you always have to subtract from it probability of A intersecting B. That's that area of overlap. You can't count twice. Y'all with me, class? I could draw the Venn, but how many understand what I'm talking about, right? Okay, good. If we got that, now you replace that part with probability of A plus probability of B minus probability of A times probability of B. And that is going to be the probability of A union B if they are independent. And so here's an example. I've got a question. Did you read this section? I mean, if you look through it, he gives some pretty decent examples that really underscore the point he's trying to make. So for this one, if we have two dice, so we have dice, basically, and we're going to roll them. So we roll the dice, and the outcomes, possible outcomes for the first die would be 1, 2, 3, 4, 5, 6. The second die roll would be 1, 2, 3, 4, 5, 6. I'm doing this one time just to make sure. Everybody follow me on this. If you look at the total number of combinations, this is just standard basic logic here. You'd start with 1, 1. This would be D1, D2, 2, 1, 3. Then it would go 2, 1, 2, 2, all the way down to 6, 6. Y'all follow me? So you're basically incrementing the first digit. First you start, the first digit is 1, then do a count here, up to 6. Then you go to the second digit. You're basically just doing something where you're counting through there. There's 36 possible outcomes. I think you all agree with that. So as far as these dice, and by the way, here, order is important. If you have a 1 in the first and a 2 in the second, that's not the same as a 2 in the first and a 1 in the second, if order is important. Y'all follow me? Even though, in terms of what dice are used for, it wouldn't matter because you wouldn't keep track of the die if you throw them on the table. So that's going to be something else we'll deal with. Then, based on that, what he's going to say is, in this one, and this is the real question, is if they're independent, this has to be true. So this is the thing we're looking at right here. If they are independent, this has to be true. So we take a look at the probability of A intersect B, and we take a look at what that is. Well, I think for the event, I didn't specify it here, but it's I think he's talking about rolling ones, but I just want to check and I'm sure. All right, so the probability for A is an odd, it has to do with an odd number. And B is going to be the number 11. So if you take a look at this, y'all follow me on this, class? We're just defining two events. If we could have defined it as anything. So A is an odd number, B is going to be rolling an 11. So for that one, probability of A is just 1/2. Y'all agree with that, class? Basically got odd and even. Each die has 3 of each. You roll them, that's without spending too much time on this. The probability of B of rolling an 11. Now, I went down here and I did the whole thing, but That's it. Do you agree with that? I mean, that would be the event. Do you agree? If you're gonna roll the die, you need a 1 in the first, oh, I'm sorry. I think he meant the sum. I gotta be careful about this. I think he means the sum, not the individual die value in this one. So if you're adding the two numbers. So for an 11, if you go down there, let's see. 11 can be 6 and 5, 5 and 6. It can be 8 and 3, 3 and 8. I'm sorry, can't have an 8. Sorry about that. 5 and 6. Then that's it. So that's 1/18. Do you agree with this, class? This is on me. So this is 1/18. And the way he's going to talk about if they're mutually exclusive, first you have to come here and take a look at the intersection of A and B. And you'll notice 11's an odd number, right? So that means the probability of rolling an 11 and an odd number happening is really just the probability of an 11. Do you agree with that, class? How many see this, basically? I mean, I'm trying to be as simple about this as possible. So that means for this, it's going to be really 1/18 or 2/36. Now, if you take a look at the probability, remember, this has to be the case. Probability of A times the probability of a B. We know that's going to be true. Do you all follow me? By inspection, correct? Now, is this true? And you can see that's going to be 1/2 times 1/18, and that is really going to be 1/36, and it means they are not independent. They are dependent on one another. This kind of makes sense. The 11 is included in the odd numbers. All right, so if 1 is included in the other set, and this isn't always true. Boy, I can think of some examples. But the way you go about doing it is this. First, find the intersection of the two events and see what the probability of that is happening. And these are simple problems, by the way. Then take a look, is that in fact is equal to that? And if it's not, they're not independent. And I think he says that in the book. Matter of fact, I'm sure he says it in the book. Okay. That's the one I want to talk about. He has a lot more detail in page 28 about in the discussion about this. So now I'm doing this, you know, it may seem obvious because I want to apply that principle to exercise 1-8.1 and 1-8.2. I'm doing this because I know it's very easy to like almost relax, not be focused, and make terrible mistakes on these kind of problems. Anyway, so this is going to be the exercises. I think, is it page 29, Darrell? At 1-8.1,
Yeah.
1-8.2. The first one is just a real general question.
Yep. Card is selected at random from a standard deck of 52 cards. Let A be the event of selecting an ace, and let B the event of selecting a red card. Are these events statistically independent? Review your answer.
I think everybody knows what a deck of cards is. All right, so there's exactly the same amount of red cards, diamonds and hearts, as there are black cards. Go with me, spades and clubs. Which means for this, down here, the probability of B is just gonna be equal to 1/2, has to be. Now, if you take a look at the probability of an ace, that's really 4 out of 52. You agree with that? This is just straight up stuff. So now, the first thing we do, I'm going to do, and this is the way I'd suggest you remember this when you come to a quiz or test. It'll become more and more like instinct later, but right now, just do it formally. So the probability of A intersect B. Now there's 52 cards, so you're drawing. And the probability that happens is really the probability you draw an ace and the ace is red. Do you follow me? That's 2 cards in the deck out of 52. Everybody agree with that? So this is going to be 2 over 52. Now, is that equal to probability of A times probability of B? That is the question. And if you look at this, probability of A is 4 over 52, and probability of B is 1/2. And in fact, that is 2 over 52. So yes, it checks the box. They are mutually independent. And I really encourage you, please do all the problems related to this in the back of the book. I may not assign them all, but you have to get, or develop like your mindset so that you can look at these problems and get almost, I guess the word used to be, does anybody speak German? Fingerspritzen. It means you have a feel for things. You know what it's the way to go about it. And you're not wondering, and that happens a lot in this course. All right, so it is. Now, the next 1-8.2, hold on for 1 second. Oh, yeah, this is good, because it's relative to the quiz. I mean, this type of problem. So this is 1-8.2. For this one, it's got a switch deal, right? And the one on top, I think, has 2 switches. I don't have to put the lever. And down here, just 1, is that right? All right, so, I mean, look, if you see something like this, these are all switches. And this is like B, and this is A, and they want to know the probability of this conducting. You agree with this, class? Now, does he give different isn't that right?
Yeah.
You see it? I mean, I want to make sure you look like I said something wrong. Is the problem right?
Yes.
What is the probability? Are they all the same? I actually forgot this.
No.
All right, so for this switch, what is it? Is this P1?
That's switch A, it'd be 0.1.
All right, I'll just call it PA. PA is 0.1. Go ahead.
And then PB, which is the first switch in your parallel, or, yeah.
Is this it?
Yeah, that's B.
PB?
Is equal to,
Is this PC?
yeah,
B and C are the 0.5.
yeah, B and C are equal to each other.
0.5?
Yeah.
And what is PD? This one.
It says probability P is equal to 0.2.
Yeah.
Let me see.
Who did he give us?
That's why I was confused.
All right, hold on. Probability A is 0.1, B is that D equals C is 0.5, and he meant, I believe, to say D is 0.2, but he has an R, I think. Isn't that what he has? Sub R, P sub R? It's supposed to be D. Probability of D is 0.2. We're going to do this problem, and I apologize for these mistakes. If I find the errata on this, I will post it on this book. You all with me, class? All right, you get this. Now, we're going to go through it, and I always talk about taking this circuit and reducing what you can. I'm going to leave it all in terms of just general, the actual values here and here. So for the first link here, this one, I'm going to just have this. Say it's equal to one link here that has a probability of PB times PC. That would be the combined, it's really because they're in series. Do y'all follow me, class? Now, the one below it here, this is just going to be PD. You agree? Everybody? All right. That's the probability of working. What did I tell you to do on this one?
To do that. 1 minus.
How do we deal? If we want the probability of working from here to here, so we can replace this stuff with one single link, what do we do?
Find the probability of it not working. and-
Right, so we start up here, right? The probability of this switch not working is 1 minus that, and the probability of this switch not working is 1 minus that. Do you all agree with that? Now, if we multiply those probabilities together, we find the probability of the circuit not working. Does everybody agree? So, when we do that, if we take 1 minus that probability we just found, that would be the probability of it working. That'll draw here. And I think everybody knows what I'm getting at here. So this switch is going to be 1 minus the quantity, 1 minus PB, PC, times 1 minus, and I'm calling it PD. And that would be a replacement for all this right here. You agree? Now we add the series element here, and that's PA, so it goes here. And this is PA, and that is the probability of each one of those switches working. Therefore, the total probability is going to be this times that. Do y'all agree? Let's see if it works. So the probability of it working is going to be equal to PA times quantity 1 minus, here's where you can make mistakes, by the way, with your parentheses, so I'll warn you about that. 1 minus PB, PC, and times 1 minus PD, and let's see, what is PA is, so that's really 0.1, and then you have 1 minus, here I have 1 minus PD, what was PD? 0.2? So that's going to be 0.8. And then this one, 1 minus PB, PC, what is PB and PC, are they 1/10?
They're both 0.5.
0.5? Okay, so this is 1/4, right? 1 minus 1/4 is 3/4. And that I don't know off the top of my head. But so you got 1/10, and then here 1 minus, and that would be 0.2 times 3, 0.6, and that's going to be 0.4 over 10, or it's going to be 0.04. I think that should be the right answer. Now, I'll tell you, because you got a quiz today, and it's going to be something related to this. You see all these bracketed terms here? Be careful about this. Try to write them out first in terms of just the general values, like I did there, and then when you go to the last step, go ahead and do the math, or the final step, do the actual mathematics where you get the single answer. But these problems, you tend to mess up because you're not attentive to detail. It's not, you don't understand, you kind of blow something. Like 1 minus 1/4 is 1/4 kind of stuff. Like the mistake I made right up at the top, adding numbers. All right. Any questions before I move on?
Do you only find the probability of it not working when they're in parallel?
Yeah, as a matter of fact, do you all remember me talking about this? In parallel, you want to find the probability of each one of those parallel, and it doesn't have to be 2. It could be 3, 4, 5. The probability of each one of those branches not working, then multiply them together. Take that number, or take 1 minus that number to find the probability it's working, replace everything by a single switch. And you can find all sorts of bizarre ways to do it. And I told you about that switch where you have something like that causes the circuit to look like two different things if it closes. Well, that one you break into two parts. First, you assume that the switch is open. Find the probability of the circuit working when the switch is open, multiply the probability of the switch being open times the probability of circuit working when the switch is open, plus the probability of the switch closed and the probability of circuit working then when it's closed. Y'all follow me? And you have to add the states. And one trick with these things too is if you put just a random number P, like P1, P2, P3, whatever it is, and you get that final answer like that, let the probability of it working go to 1. You better get 1. And then let the probability of it working go to 0. You better get 0. You all follow me on this? And that way you can have a check that you didn't make something stupid, make a mistake. And there are a lot, especially early in the morning is when I'm most dangerous to make mistakes. And I know until I have some coffee, I wish I had some coffee, I'm liable to make stupid mistakes. You almost have to be extra attentive when you're a little tired to these things. All right, we're not done. I am spending a lot of time going through these exercises because in this particular chapter, there's some wrong values here. All right, next is going to be combinational experiments in section 1.9. And here, he gives you he starts out in this section and says that, all right, suppose we have a coin toss and we have die. We roll die. They are mutually independent, right? All right, but these are two events that are taking place, and we're going to say the coin toss happens, there is an outcome. The die rolls, there is an outcome. And now we're going to ask questions about all these things. And these are independent, but they're combined experiments. And, you know, if the outcomes don't have to do with a single die, the outcome, or a single coin, if there are more things involved, then they're called combined. And for this stuff, first, he mentions this in the book. I'm going to do it really quick, and I don't think you'll have any problem with this. If we talk about tossing a coin and rolling a dice, and you created all possible outcomes. So for the coin, the only thing you can have is a heads or a tail. For the die, single die, you're going to have the numbers 1 through 6. If you wanted to represent this, and in the first couple of, in the chapter 1, he'll actually ask you to write out all possible values so you get a visual on what is possible. If you look at this, you could have a head, right? Head, can keep going down. And you would have for the die outcome 1, 2, 3, 4, 6, right? Or you can have a tail in the same deal. Tail, 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 tail. And it would be 1, 2, 3, all the way down to 6. The total possibility, all possibilities considered, is going to be something where you have a total of 12 possible outcomes. Now, they are combinational. Do you agree with this, class? That's the only thing it can be. It's discussed in section 1.9 in the book. And did anybody look at these exercises? I don't think I signed them. All right. Here, they're wrong answers. And I apologize for them. So really, if you want to know, suppose you have something where you have 2 events, and the first event has 6 possible outcomes, the second has 10 possible outcomes. The actual number of possible outcomes with the combinational stuff we're talking about is going to be 10 times 6 or 60. If you just, you can see the progression of what I just did. It's going to be 60. If you had 3 events it would be the first event, number of outcomes, second event, number of outcomes, third event, and so forth. You can take this and extrapolate it ad infinitum. That's just the possible outcomes. From that, all possible outcomes, you start deriving what the probability is of the events he's defining, the intersect of A and B kind of stuff, or A, B, and C. So for this one, now, if you have access to this, I'm gonna do this. This is 1-9.1, but it's the exercise. Do the problems too, but if you look at this, I'm going through this a little quick. I'm not going through a whole lot of all the problems in the back, but most of them, if you see these things, they're fairly easy. Can you read that for me?
A combined experiment is performed by flipping a coin 3 times. The elements of the part space are head, 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 tails, head, tails, head, etc.
All right, this is for the coin. Hold on for 1 second. Yeah, we know we can get three times, right? Heads, 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 tails, heads, tails, heads, so forth. All the way down, you're gonna have eight of them until you get tails, 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 right? Right, now what does he say?
Write all the elements of the Cartesian product space.
And what was the other thing? You toss a coin?
Yeah, you flip a coin 3 times.
This is, yeah, all right, so this is a coin, and this is all possible outcomes, right? What else next?
Find the probability of obtaining exactly 1 head.
Now, this is just looking at the event space. For 1 head, maybe I should write them all down. I should have started with the tails. Then you got head, head, tails. Let's do it this way. Start with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's 8. And the 1 represents heads, the 0 tails, right? He wants 1 head, right? Now, here's where the book's answer's wrong. Okay, doesn't he ask for that 1 head? Take a look at this. Here's 1. But you can see, is it staggering here? There's another, and there's another. So it should be 3/8, and he has something else.
It has 1/2 or 1/4.
Yeah, you see, that's 3/8. What else? What's this? You see it? Do you have access to this stuff, everyone? All right, if you look, that answer's wrong. Here's 1/4. What's the next part of that one?
Find the probability of obtaining at least 2 tails.
All right. And again, this is just inspection here, right? We know total number of outcomes is 8. Now what's the probability? So this is the probability of simply only 1 head. Does it say only 1?
This is exactly 1.
Yeah. All right. So now the probability of what?
Obtaining at least 2 tails.
All right, this is at least 2 tails. At least 2 tails. Tails are 0. All right. So, and I'm going to just stick to this. It's a nice small number. There's only 8, and you just look down and figure out which ones have 2 zeros. At least 2 zeros. All right. So we could have 3 zeros. All right. So because we can have 3 zeros, this one counts. Right. Then this one. Then this one. And that's it, correct? Pardon me?
Third one.
0, 1, 0.
From the top, third down. It's the one that's already circled.
Yeah, sorry, that's 0, 1, 0. I'm sorry, I didn't do that. Yeah, correct, class? If you look at that, there's 4, and there's a total of 8. So at least 2 tails, and that should be 4/8 or 1/2. Does he have that?
Yeah, I think it's 1/2 is the answer.
Okay. But the first one's wrong on that one. Okay? Just to be sure. I'm gonna get to this next one. So, that is, finally, we're gonna get into Bernoulli trials. Have you all heard about Bernoulli trials in your mathematics courses? How many have? Let's see, your hand. You don't remember? I mean, that should have been in your math courses, I think, but I'm not sure which one you get it in. This is a real important concept for electrical and computer engineers and engineering in general, as well as physics, math. But I want to tell you that, first let me define what we're going to be talking about. And for this type of an event, we're going to say the experiment's going to be repeated over and over and over again, and the probability is not going to change throughout the experiment. For instance, rolling a die, and say the event that we're looking for is a 1. All right, so the probability of that is 1/6. Take the die, roll it again, roll it again, roll it again, roll it again. Now, what is the probability if you roll it n times of exactly k events happening that correspond to rolling a 1? Do you all follow me on this? This is the idea behind it. Let me just show you this. If you take a look at something and you want to find out how many different ways you can actually organize, say, the way, I'm trying to think how he does this, or what he discusses with. But if you have n objects, okay, I mean n, say, make n equal 3. If you have 3 rolls of a die, how many different ways can you organize possible outcomes? I mean, how many different outcomes are there? Well, the total number would be what? 6 times 6 times 6, 36 times 6. Total possible outcomes. I mean, if you look and just, all right, now, of that, what is the probability of getting a 1 3 times? 1/6 times 1/6 times 1/6. Because really, and this is just simple probability, but if you wanted the probability of getting at least 2 1s, that means you could have 2 1s and 3 1s. Do you follow me on this? Now this is the combinational thing. So I'm just going to write it down. I'll try to explain it a little better in a second without getting too far into the permutation space. When you take a look at first, this is a symbol of, and this is heat. I'm not sure what the term is. And this is a binomial coefficient, I think, in his. And if we have nk, that is an n, by the way, and this is going to be a k, that is n factorial over k factorial, n minus k factorial. And the way I think of it is, if you have k, you want to take k items at a time. K could be a 1 or something like this. Out of n tries, how many ways can you organize that? Do you all follow me on this, class? So if you want 3 heads out of 5 rolls, how many ways could you organize it? Well, you could get head, 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 and then tail, tail. You could get head, tail, head, tail, head. Do you all follow me? So if we take, and these are binary outcomes, it's either one or the other. Either it happened or it didn't. With me on this, class? Now, do you all know what a factorial is, everyone? How many do? I'm assuming y'all do, but I've learned my lesson about these things. A factorial, the one thing about a factorial, if you have like 3 factorial, that's 1 times 2 times 3. That's all it is. But you also have to know that 1 factorial is 1 and it makes sense. And 0 factorial is 1 as well. Those are the one thing you have to make sure. 0 factorial is 1. With me on this? So this is the number of ways you can take k items from n total. Number of different ways you can organize them. Now if we take a look at the probability, and this is important, write this down, it's the Bernoulli trials. If you take a look at the probability of pulling k items, meaning the total length or the total number of experiments is n, and this is in the book, it will become n factorial over k factorial, n minus k factorial. But then there's an add, that's just the binomial coefficient. Then next to it, you're going to have this p here represents the probability of a positive outcome. Do y'all follow me? Whatever it may be, positive outcome. And it's going to be to the power k. And then the probability of a negative or of it not happening is q. And the easy way to do this is just make q equals to 1 minus p. And here it would be to the n minus k. Now I'm going to get into this and apply it. I can tell you this much. In his book, in section 1.9, he'll talk about proving this. And we could prove it. We start with, if we have 2 items, how many different ways can you take 1? All right, and you can just take it logically. Well, you could have, if you have 2 items, a 1 and a 0. You could have 1, 0, 0, 1, period. You all follow me? You know, it'll play out with these things. So I'm going to use this theorem, and this is, by the way, your calculators can do this, by the way. I hope you all have your calculators here today. Your calculators can calculate this actual value here using Bernoulli trials in the statistics package or whatever you call it. You can take a look at this. I'm not asking this today, but on your calculators, they have something in it will either be called Bernoulli trials or to have a statistics package. And you'll have something like P of n, comma k, or k, comma n, depending on the kind of calculator. I'm just cluing you. Your calculator is a godsend on this one. But I do want to tell you some large numbers give you problems, and I'll show you what I'm talking about. So let's just apply this to a simple example. Suppose I take the coin toss, all right? So if I have a coin toss, and I want the probability of getting 3 heads, and I roll it 5 times. You with me on this? So a positive outcome is a head. Now this is exactly 3 heads, not more or less. If I take a look at this, so the probability in his book, I gotta be careful of one thing. He uses P of n, sub n, k. What he does is have this, P of n, that means the number of trials, and k are the number of positive outcomes from these trials. They can be called experiments or trials, they're the same thing. With me? You look at this, you start by saying, well, the number n here would be 5. I'm going to basically toss the coin, I should say toss, not roll. Toss a coin 5 times. I want to find out the probability of having 3 heads out of 5 tosses. Just that, with me? So here I'm going to go ahead and I'll take n factorial, 5 factorial, over k. K is 3 factorial. And then I have n minus k. That's 2 factorial. Then I have p. Well, the probability of a head or a tail is the same. It's possible. That's one of the reasons I chose this. So this is going to be 1/2. And since I want k positive outcomes, it's going to be to the 3, and the remaining is going to be 1/2 to the 5, or to the, sorry, 2. It's going to be 5 minus 2. With me on this, class? This is just a simple application. You go through this one, and I'll tell you, this particular problem, these numbers are easy to deal with. Your calculators won't have any problem. Here's the problem with your calculator. It can be a problem unless it's adapted to it. Suppose this is 500. 500 factorial is an enormous number. Right? Suppose it's 500 and I want to take 30. With me? Here we have problems, or maybe not 30, say 400. Well, when you take 500 factorial, you're that would be 500 times 499 times all the way down the line. If I want to find out how many different ways to take 400 positive outcomes there, over 400 factorial, what I would do is get rid of everything, because that would cancel the 1, 2, 3, 4, up to 400, and this top part would become 500 times 499 down through really 401. Follow me? It's an easier mathematical operation, but your calculators may have this thing that's an approximate way of estimating those values for very large numbers. But if you try to do this yourself, you go a little nuts with your calculator, with the older ones at least. So this one is going to be 5 factorial over 3 factorial, which means this is 3 times 2 times 1. This is really, it's going to be equal to 5 times 4 times 3 times 2 times 1. So I get rid of the 3 times 2 times 1 stuff, and I get 4 times 5 here. Then it's really 4 times 5, or 20. 2 factorial is just 2. And then I get 1/2 to the 5th power. So that's 20 over 2, or 10. And it's 10 divided by, and that should be 32, right? Y'all with me on this? So that's an example of it being applied, taking 3 heads out of 5 rolls. Now if you want the likelihood of rolling 3 heads or more, you would have to add to that the probability of 5 factorial over, and now you're going to get 1 factorial, 4 factorial. You all with me on this, class? Times this stuff, and the probability of having no heads. And that's, and when you do this, what happens is these terms cancel. Then you basically have n factorial over 0 factorial, and this becomes n factorial. They cancel, and you're just over here. Just multiply those two together. And it will be exactly 1 over 2 to the 5th for that problem. And you'd have to add those probabilities to get the total probability of that happening. Now, let's go to a much simpler one. Suppose we're going to apply these Bernoulli trials to one thing. Tossing a coin 3 times. This should be logical, I'm about to do. What's the probability of getting just 1 head? With me? So here we're going to do this. And I'll put the subscript here, so we're going to toss it 3 times, and we're going to have k equal 1. You'll see these things work perfectly. So n is 3 factorial. Then that would be 2 factorial over 1 factorial. First, does everybody agree with what I'm doing here? I'm just applying that formula. N is 3, k is 2. Okay. Now, what's the probability of a head or tail? Well, this is the nice thing about tossing a coin. If it's a fair coin, they're both the same, the probability of head or tail. So the probability of a head is 1/2. Here I want one of them, and the probability of tail is 1/2. N minus k is going to be 2. And that is, if you look at this, well, 3 factorial over 2 factorial is just 3. It's 3 times, and this is going to be 1 over 8. So it's 3/8. We did this problem a second ago when we were talking about the likelihood, that was the head-tail problem earlier. And it is 3/8. That's the right answer. Can you all follow me on this? This is applying Bernoulli trials. There's a lot more to this, but I wanted to cover that point today. Now for your quiz. All right, so what I do with everybody, I separate you, and I want at least 1 row between you and your neighbors, so do me a favor. Why don't you guys move over to that area. You can stay. You guys stay. You move over to, how about everybody move to the last row? You guys, there's 1, 2, 3 seats. Just take a desk and push it over there. I want as much space between you and your neighbor as possible. Now this is closed book, closed nuts. Are you going to just sit down there? And so just take your phone out too. Put your phone out and put it on the desk next to you, upside down. First quiz is always fun.
When you get it first